Welcome to this video that has two different purposes. The first is to present to you a real-life SLAM application that turned out pretty well, and also to give you an example of a master thesis project that's been performed within the framework of this course and that turned out to be a success story. To start from the beginning, this was a master thesis project at FI in 2014. The student that took it had taken the course and thought that SLAM was a cool idea. FI had interest in indoor positioning for first responders, in particular smoke divers, as the guy on the right here. And that's because smoke diving is a really dangerous business. So you send in people two at a time in a building to dive in smoke. They basically don't see anything, it's burning all over the place, and the risk of actually getting stuck and injured in there is quite high. You want to know where these smoke divers are with as high accuracy as possible so that you can go in and get them if something goes wrong. Unfortunately, it's difficult to use conventional positioning systems for this because GNSS, or in particular GPS, that's commonly used outdoors, do not work indoors very well. Indoor solutions that rely on Wi-Fi and similar are usually not accessible because the first thing that you do when a building is on fire is to turn off the electric power, not to cause more fires in there. It's also not always possible to get floor plans for different buildings in a rush. So you want to be able to send in people to know where they are as accurate as possible if you need to get them out, and also for them to be able to, in an efficient way, tell the next team that's coming after them where they've been, so that you can search the building as quickly as possible, not missing anything, but at the same time not doing double checking, because the more time you spend in there, the more risk that you get injured. Requirements is basically you want to have room level accuracy, so a couple of meters. You need to be independent of previously installed infrastructure, maps, and other things that could be difficult to get in a rush. And it needs to be fairly cheap, small in size, and not way too much, because these guys anyhow carry way too many things in with them in the building. So the thing that we came up with was to try to use opportunistic radio signal strength measurements. So what you usually do in indoor navigation applications is to pre-map the building that you're interested in. You map the Wi-Fi access points that you can listen to from different positions. You see how strong they are and their IDs. And then when you revisit the same place, you can see, okay, this is the signature that I saw last time I was here, so I must be here. In this case, we considered to make this a SLAM application to be able to build a map on the fly. We intend to use opportunistic radio signals, which is, say, radio signals from radio broadcast, TV broadcast, and similar things. You could also consider adding a antenna broadcasting signals on the fire engine, for example, to improve the situation. But hopefully you could just rely on infrastructure that's already there in the global sense. We then rely on load closure to avoid the drift, and make a map of the RSS as we walk around. You can see two examples of how the RSS from two different sources vary during the same motion in a building, and in the middle you see the equipment used by the master's thesis student to collect this data. So it's a normal Wi-Fi antenna on the leg and a software-defined radio collecting the data from it. We will use 7 different sources in the example, but we could use more or less depending on the accuracy you need and the situation in total. To start with, we decided to use a Gaussian process to model the differences in the radio signal strength throughout the area that we were working in. That will be our map. The Gaussian process is a way to represent a function from machine learning community. It's a bit too involved to go into details here, but you could view it as all separate positions in this case give rise to a function value, and they're all considered as a joint Gaussian distribution. The method supplies us with the mean for the function in each position and an uncertainty covariance. Different positions within this area that we consider are connected with a covariance function, so they are not completely independent but connected to each other with this kernel. We can train this representation using measurements that we obtain throughout the mission. We also in this case use a sparse approximation of the radial basis function for the kernel to speed things up, but that's more or less a trick just to get things to work. The important thing here is that the GP can then afterwards be used to predict what kind of measurements we would get with respect to the radio signal strength for a specific position in the area. We also need a method to determine how we're moving around in this area. So for this we choose to use a foot-mounted inertial navigation system. I'm not sure if you can see it, but taped on the foot here of the master students, we have a box roughly the size of a matchbox that includes accelerometers, gyroscopes, and magnetometers. And more or less we can double integrate the accelerometers to get the position of this little box and hence the wearer. Unfortunately, doing this will add up to large errors immediately if you just do a simple dead reckoning. However, by noticing that when the foot is on the ground in the step, it's still, we can get a measurement that has zero velocity that can correct the drift. This gives us a method of positioning that's fairly accurate, surprisingly accurate actually, and where the distance traveled is fairly good, but the orientation, the heading, is not so good. Again, the component itself is something that could render a couple of movies like this, but we use it as a component in the SLAM application. So describing the motion based on this, we have a constant position model driven by this odometry from the foot-mounted INS system. You see here that basically we have our current position plus the distance traveled and the direction we traveled it in. Furthermore, there's two state components that represent the drift in the heading and the derivative of that. So we have a constant velocity representation for the drift. You see the measurement from the INS here that we use as input to the filter here. That gives us a state space that comprises the global position of the wearer and an estimate of the heading error in a CV form. There's a lot of other things that could actually have been extracted from the INS system, such as velocities, angular rates, and things like that. But for simplicity, we kept them out and not to be too dependent on the specific implementation of this component in the system. As it turns out, this is enough for the problem. In putting it all together, we used a distributed particle filter SLAM algorithm for the task. We gridded the area that we were working in to get an occupancy grid-like representation of the map, where each grid has its own representation of the RSS that it expects to get from these different frequencies. We use a trick to speed up the computations using an ancestry tree when keeping track of the particle history, which is necessary for representing the full trajectory in a good way. We also used some tricks with efficient data structures and stuff like that, and different tuning knobs required to keep the memory and computational complexity down enough to be able to run this in real time. And this is, of course, part of the master thesis work to deal with all these things. Now let's look at an illustration of the result of the master thesis and the final algorithm. You might recognize this as the A building. And the student worked around here with this foot-mounted INS system and the antenna on his leg, then collecting data, and then he did some post-processing offline, but in real-time speed to try to position himself. The map here is only included for reference so that you see that things are working out in an appropriate way, and was not used for the algorithm. It only used the foot-mounted inertial navigation system and the measurements from the antenna. In the movie that I will show you next, you will see a green line. It represents the estimate of the foot-mounted system. You will see red dots representing the particles at the current time. And you will see a blue line representing the trajectory estimated by the particle filter. You will see that the trajectory of the particle filter updates over time, also back in time, so to say. And that depends on compensating for the changes due to the resampling at the current step. And here we go. We're walking, let's stop it there. So let's see, we have been walking for a while. We see that the blue and the green is roughly the same. We see that we have spread the particles to represent that we know pretty much how far we walked, but not the direction. That's the banana shape. Let's run a bit more and see what happens when we start to get the loop closure. So as we go on, we spread the particles more. And there we're starting to get lobe closure while we walk down and then up again. And you can see how I actually start to compensate the trajectory to better match what is the truth. And we can see that it's better because it better match the map. Let's continue running. We get more lobe closure and the thing shakes better and better, so it's now fitting the map pretty well. See how the particles are also sort of gathering in one spot, depending on how much information we get. And there we have the final result. It's pretty good. Funny thing to note here is that some freezes in the movie. It's not due to problems with my displaying of the movie. It's actually the student that has to stop to tie his shoelaces. I also think that's worth noting how much the foot-mounted system has diverged. The green curve looks roughly right, but it's all skewed up and rotated, all wrong. Whereas the blue curve representing the particle filter solution, when we have used radio signal strength measurements, fit the environment pretty well. So all in all, a very impressive result. I'll round up not with a normal summary, but with the outline of the outcome of this master's thesis. So of course, I have described this method of a SLAM application that worked out well. We used some other measurements than we have discussed in the course, but it shows the applicability of the theory that we've been discussing. Even more fun, I think, is to discuss the outcome of the master thesis itself. It was quite successful. We managed to send off the results to a conference in the field on indoor position and indoor navigation, one of the major ones in the field, where the paper ended up as the runner-up for the best paper. So it's a good sign. I also sent this master student's report to Radionavigationsnämnden, where he won the Best Thesis Award. And he was also the runner-up for Dataföreningens Best Master Thesis Award. So all in all, quite successful work from Martin Nilsson at FOI in 2014. If you want to read more about the thesis, the master's thesis, you have a link here, and you can also read the paper. We are still doing research in this area today.